Hello and welcome to Controllerstech. Today we will start a new series covering the ADC peripheral of the STM32 microcontrollers. We will cover different ways of reading the data from the analog devices throughout this series. This is the first video of the series, and today we will see how to configure the ADC, and how to use the polling mode to read the single channel of the ADC peripheral. I will use the STM32 ADC1 development board throughout this series, but we will also see the configuration available in the F4 series and STM32 F103 series MCUs. The STM32 ADC750 and ADC743 development boards are available on the Controllerstech store, so you guys can purchase these boards from there. Let's start the Cube IDE and create a new project. I am using STM32 ADC750 VBT6. Give some name to the project, and click Finish. Let's see the schematics of this board before proceeding forward. Here you can see that there is an external 25 MHz crystal available on the board. We will use this crystal to provide the clock to the board. Let's open the ADC configuration, and enable the high-speed external crystal. We will configure the clock in a while. Let's enable the ADC first. The channels 0 to 2 are not available, and we have channel 3 as the first channel here. The ADC can be selected in either differential mode, or the single-ended mode. We will cover the differential mode later in the series, so for now let's select the single-ended mode. Single-ended mode is basically the usual ADC we have available on other STM32 boards as well. Let's configure the clock now. This board has 25 MHz crystal, so set the value 25 here. I will use the PLL to run the system at maximum possible 480 MHz. Let's see the configuration available on the other STM32 MCUs. Here I am creating a dummy project on CubeMX. We will see the configuration for the F446RE. Let's enable channel 0 of the ADC. Here we do not have the option to choose the differential or single-ended mode. The ADC by default is using the single-ended mode, and we can't use different modes with this MCU. We will see the rest of the configuration in a while. Let's go back to our project. Here you can see the ADC clock is at 75 MHz right now. The ADC peripheral is using the clock from PLL2P, so we can modify it here to vary the clock fed to the ADC. You can even change the ADC clock source, but I will leave it to the default one. Now let's take a look at the F446 clock diagram. Here we don't have a separate clock data for the ADC. To know the ADC clock, we need to check the datasheet of the MCU. Here look for the block diagram, which basically contains the clock configuration. As you can see, the ADC1 is connected to the APB2 bus. If you look in the clock configuration, the APB2 clock is at 16 MHz right now. This makes the ADC clock also at the same frequency. Let's come back to our project now. We have enabled the ADC1 channel 3, and hence the pin PA6 is selected as the ADC pin. We will connect the potentiometer output to this pin. Let's configure the ADC now. The mode is set to independent mode, because this ADC is working independently right now. We can use the combined mode by enabling another ADC as well, but that will be covered in the future videos. The ADC has the configurable resolution, which can be set between 8 bits to 16 bits. The resolution configuration is also available on the F446, and here we have the options to choose between 6 bits to 12 bits. But all the STM32 MCUs do not have the option to choose the ADC resolution. Let's quickly see the configuration for the STM32 F103C8. Let's enable the ADC1 channel 0. you can see we do not have the option to choose the ADC resolution. In such cases, you can refer to the reference manual of the MCU you are using. Here, if we check the ADC section, it is clearly mentioned that the MCU supports 12-bit resolution only. Basically, we can't choose the resolution, it is fixed. In today's video, I am choosing the 16-bit resolution for the ADC, and hence the ADC data will vary between 0 to 65535. Next is the scan conversion mode, which is used while using the multiple channels. We are using a single channel only, so let's leave it disabled. The continuous conversion mode enables the ADC to start another conversion as soon as the first conversion is over. Let's keep it disabled, so that we can see the difference. The discontinuous conversion mode is just the opposite of the continuous conversion mode. The end of conversion sets the flag when either a single conversion is completed, or a sequence of conversions is complete. For a single channel, we will leave it to single conversion only. I will leave the rest of these to default, we will see their usage in the future videos. The channel configuration can be found under the rank section. The channel is set to channel 3, as we have enabled only that. The sampling time is basically how long the ADC will take to sample and convert the data. We will cover the ADC sampling and conversion time in a separate video, let's set it to maximum for now. That is all the configuration we need. Let's check the configuration available in the F103C8. Here we have the data alignment, which is set to right align. Since the ADC has the resolution of 12 bits, the data can be only stored in the 16-bit variable. This data alignment basically sets whether to align the 12-bit data to the right of the array, or to the left of the array. Then we have the scan conversion, continuous conversion, and discontinuous modes as usual. Under the rank section, we have the same option to choose the sampling time. Now let's quickly see the configuration for the F446RE. Here we have the clock prescaler, which can be used to further divide the APB clock, so to reduce the clock fed to the ADC. For example, the APB2 clock is at 16 MHz right now, and if we use the prescaler of 8, the ADC clock will be reduced to 2 MHz. Then we have the option to choose the resolution, the data alignment, and the conversion modes. We have a new option here to enable the DMA continuous request. This is basically used when you want the DMA to continuously receive the data from the ADC peripheral. This option is not available in the F103C8 MCU, so there you can simply enable the DMA, and it will automatically fetch the data continuously. Here under the rank section, we again have the same options to choose the sampling time etc. We also have the option to choose the prescaler in the H750 MCU. For example, the ADC clock is at 15 MHz right now, and if we use the prescaler of 10, the ADC clock will reduce to 1.5 MHz. Alright, that is all we need for now. Click Save to generate the project. Here is the picture showing the connection between the potentiometer and the board. The VCC from the potentiometer is connected to the 3.3 volts, ground is connected to the ground, and the data pin is connected to the pin PA6. Alright, we will start with the polling mode to get the ADC data. Let's define a 16-bit variable to store the ADC data. We want to get the results continuously, so we will write the code in the while loop. First start the ADC. Then poll for the conversion to complete. We will wait 100 milliseconds for the ADC to sample and convert the result. Then read the ADC value and store it in the variable we defined. Finally stop the ADC. Let's give a delay of 500 milliseconds between each call. We will also increment the count variable, so to make sure if everything is working all right inside the while loop. Alright, that is all we need to read the single channel ADC using the pole for conversion method. Let's build the project, and debug it to see the variable value. Let's add ADC value, and the count variables to live expression. You can see the variation in the ADC value, the fluctuations in the ADC values are normal. The count variable is incrementing every 500 milliseconds, so our while loop is working normally. Now let's slide the potentiometer to the other end. You can see the ADC value is incrementing as well. Now we are somewhere near the middle, and the ADC value is around 39,000. Let's keep sliding it towards the other end. Now we have reached the other end, the resistance of the potentiometer is maximum at this point, so is the ADC value. Since the resolution is set to 16 bits, the maximum value is 65,535, and it is what we got here. So the ADC value is varying as we slide the potentiometer, but we are not quite getting the value 0. At the lowest point, the ADC value is 1700. This is fine for now, as we can still refer to this as our lowest value. Some of the STM32 MCUs support the ADC calibration, we will talk about it in the future videos. Now let's assume that we want to map this ADC value to some specific range. We can use this map function, which I took from the Arduino source code. Call the map function after the ADC value has been captured. The output will be stored in the value variable. We want to map the ADC value, the minimum input value is 1000, the maximum value is 65,535, and we want to map it between 0 to 100. Actually the minimum input value should have been 0, but since we are only able to achieve 1700 with our ADC, I am setting it to 1000. Anyway, let's build and debug this project again. We will add the value variable to the live expression. You can see that the value variable is incrementing as I am moving the slider. It is towards the middle now, and the value is at 58. And when we move it towards the end, the value has reached 100. It is the maximum output value we set in the map function. So we can use the map function to get the output in terms of voltage, or in percentage resistance. So the poll method to read the ADC data is working fine. In this polling method, the CPU is blocked for the ADC operation and we cannot perform any other task during that time. This is where the interrupt comes in. We will cover the interrupt and DMA in the next video. I hope you understood how to configure the ADC to use the polling method. The polling method does block the CPU, but this is good enough if you do not have any time-sensitive requirement from the ADC. We can use this method in combination with the RTOS to read the ADC values every few milliseconds. This is it for the video. You can download the project from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.